also from my side. Thanks for coming out. I would like to take all of you to a journey of the sperm from his ejaculation to fertilization. So the main character of today's talk is the sperm. That was too fast. There you go. Is the sperm Frederic. Frederic pretty much consists of two components, a head and a tail. Very simple. Actually, the best analogy for a sperm that also my PI likes to use, louder? Okay, is a rocket ship. The rocket propulsion down here is the tail that makes Frederic move forward, and instead of cargo up here, that's like machine and instrument, humans, Frederic contains genetic information in his head, so-called DNA. Frederic turned out a little bit unproportional, so to do the beauty of the sperm justice, I brought also pictures of real-life sperm for you, and I worked with both human and mouse sperm. So here you can see a human sperm that's around 50 micrometer long. Since we are at the scientific talk, I hope you don't mind that I use the metric system. Then here on the right-hand side, you see a mouse sperm that's 3 times longer, about 150 micrometer long. In addition to their size, you can also see that they look quite different because human sperm have a rather round, light bulb-shaped head, whereas the mouse has a more sickle-shaped head with a hook here at the front. You can also appreciate that the sperm length is not proportional to the body size. So the mouse is much smaller, but the sperm are actually bigger than human sperm. The biggest sperm length found in the animal kingdom is actually found in the fruit fly. The fruit flies are those tiny 3 to 5 millimeter flies that hang out on your fruit in the summer. So you can see here 200x magnification of a fruit fly, and this sausage here is its genital tract, which is a little bit morbid. I know that's the best image I could find. And then here on the right-hand side, you see that its sperm is 5.8 centimeter long. This is around 205 bigger than the animal himself. And this works because you see that the sperm is curled up quite a bit, so therefore it doesn't use up that much space as if it would be stretched out completely. So Frederic and his fruitous 30 million brothers has been given the task to deliver the genetic information in here to the oocyte. So I took the liberty of calling the oocyte Susanna in our scenario here. You might think this is quite easy. It might rather be a piece of cake, right? So Frederic ends up down here after ejaculation. He just has to swim up here through the uterus, through the so-called follicular tube, and then up here, Susanna is waiting for him. It's not that easy. In the next couple of slides, you will hopefully understand why. You already know that Frederic is only 50 micrometer long. The distance he has to overcome is 20 centimeter. So you can imagine that better. I converted that into human dimensions. So we have here a regular swimmer of around 1.8 meter height. That swimmer has to swim 7.2 kilometers. So that's roughly from the tip of Manhattan to the tip of Roosevelt Island. The human world record holder, Sun Yang, who made the world record in 2012 in London, I believe, would be able to swim this distance in an hour. Frederic makes that in 30 minutes, so he's considerably faster. Now, in contrast to Sun Yang, who knows pretty well where he has to swim to, Frederic has the ability to either swim up the East River, or he could also swim up the Hudson. So this represents the two tubes that we have in the uterus. So if Frederic is unfortunate and decides to swim up the Hudson, he ends up here, and then he looks pretty stupid because there's no oocyte waiting for him that he can fertilize. So this actually happens to 50% of the sperm that are ejaculated. Half of them are just simply swimming the wrong way. Then in contrast to the uterus, to the swimming pool, the uterus is pretty dark. And in contrast to this picture here, Frederic doesn't have any eyes. So he doesn't know where he has to swim to. It's getting worse because the uterus is not filled with water, it's actually filled with a mucus-like substance that's pretty much like jelly. Then to top it all off, you see those fine hairs here at the uterus wall. This mucus is actually pushed against the swimming direction of Frederic. Those round cells you see here are immune cells that have to kill him off. So combining those slides, Frederic has to swim faster than the human world record holder in the dark without eyes against a flow of mucus. Now it doesn't sound that easy anymore, right? So meeting between Frederic and Susanna sounds rather like a mission impossible. Well, fertilization sometimes works, and all of us here sitting are actually living proof. So to understand how Frederic makes his way to Susanna, we have to go all the way to his birth. So this is baby Frederic. Frederic is born in the seminiferous tubules, so those tubules here, in the male testis. So here the skin has been removed from the testis, and you see that the whole testis is built up from these tubules that just fold and wind many, many times, so they build up that three-dimensional space. If we cut one of those tubules in half, we see this. So this here is the basal lamina, the plasma membrane, so the membrane that surrounds those tubes. Then here in the periphery, the so-called spermatogonia are sitting. Those are sperm stem cells that divide over and over and over endlessly, and thereby a healthy male can produce around 1,500 sperm per second from puberty to his death. Those sperm then travel through the lumen, so this cavity here in the middle, and while they travel through that area, they elongate. So here in the human, you then have the finished sperm. So here's the head, and then the long tail. In this fluorescent image, hopefully you can see again in blue, the stem cells here, and then here in green in the middle are the finished sperm. When the sperm are finished, they are then pushed through the testis in another tissue with a more complicated name, the so-called epididymis. So they start here and then they pushed all the way up here, where they are stored till ejaculation. While they travel through the epididymis, they actually undergo a maturation process. So in the beginning, Frederic is that immotile sperm that can't swim or can't talk or walk, if you want to talk about babies. And then through this maturation process, he ends up as a motile teenager, so to say. So then the whole bees and flower thing happened, all what I'm talking about. And then the sperm end up here in the vagina of the female. The first thing Frederic comes in contact with in the uterus is a molecule called bicarbonate. So you see here it consists of a C, and then there are 3 oxygens, and then there's a proton. All of you who like to bake like I do have actually used it before, because this is essentially baking powder. What bicarbonate does is that it activates a protein that is called soluble adenylate cyclase. That protein is actually the reason why I came to New York, because my whole lab that's sitting over there, okay, is trying to figure out why this enzyme or protein is important and how it works in different cells and tissues. Soluble adenylate cyclase is not only a protein, it is also an enzyme. What does that mean? An enzyme is a protein that takes a specific substrate, I've drawn it out pretty easily down here, and that takes that substrate and converts that substrate into 1 or 2 or multiple specific products. So it's pretty much like a scissor, or you do arts and crafts with a substrate, and then a product ends up at the end. The specific substrate for SAC is called ATP. You might have heard of that before, because that's the energy current in the cell. So it consists of a base here, then this down here is a sugar, and then there are 3 phosphates attached to it. So this is the first one, the second one, and the third one. So when SAC is activated by bicarbonate, it takes this ATP and converts it into a specific product, and that product is called cyclic AMP. They look pretty comparable, right? So it still has this nucleotide here, it still has that sugar, but there's only 1 phosphate left, and that phosphate is actually turned into a ring. That's why it's called cyclic AMP. This cyclic AMP is a so-called second messenger, and now another weird word that you don't really understand. A cyclic messenger is, as its name already applies, a small molecule that transports a message in a cell. So it's pretty much comparable like the intradepartal memos they used in the Harry Potter movies. So, see, AMP is produced here at the periphery of the cell when SAC is activated by bicarbonate, and then that the AMP travels through the cells, and then when it finds target proteins, it activates them. One of those target proteins is called protein kinase A. Whenever we call something a kinase, then that's an enzyme that adds a phosphate to another protein. So Frederic, in the end, looks something like this. So he has phosphate group attached to proteins all over his body. This is a very crucial maturation process again, because this converts Frederic from a teenager that would not be able to fertilize Susanna in a fully fertile adult. In the sperm world we call that capacitation, but you don't have to remember that if you don't want to. Those phosphorylations are really hard to show, but what I can show you is that Frederic beating patterns change through this maturation capacitation process. So here you see a sperm attached to a cover slip with his head, and you see his flagellum freely beating around. Now when bicarbonate is added and that whole capacitation process is induced, this increases his flagellar beat frequency quite considerably. So I hope you can see that. It's just beating much faster than before. It's so fast that you can't really follow anymore where the flagella is while it's beating. You can imagine that this whole increase in beat frequency costs quite a bit of energy. So one of those proteins that are phosphorylated by the protein kinase A are actually proteins that regulate the energy production in the cell. So what actually happens is that this protein kinase A activates those proteins, and thereby more ATP is produced. I'm mentioning this because this is actually what I'm studying in the lab. This is my daily bread and butter. So I try to figure out how sperm produce energy. So this is more specific, but whether they use glycolysis or oxidative phosphorylation, and how SAC regulates those processes and this increase in energy production. So, and then we have more ATP, more energy, and thereby this whole increase in beating pattern can be supported. So now we still have the problem that it's dark in there and Frederic has no eyes, so he can swim faster, but he still doesn't really have an idea where he has to go. I told you before about that mucus that is pushed into the direction where Frederic is swimming, and believe it or not, this actually helps him to find the oocyte. So in these videos you see sperm swimming around when no flow is attached. So you see they pretty much all swim all over the place, they don't really know where they're going, they're swimming in circles also sometimes, so you can imagine that they don't really get anywhere. Now a flow is applied from here, and you see that the sperm start swimming in straight lines. So this one, this one, this one. So most of them are actually having a direction now. So now nature and the uterus is really smart because the flow is coming from the location where the oocyte is localized. So that means when the sperm simply align themselves against that flow, they automatically swim into the right direction. And this whole process is called rheotaxis. So by using this rheotaxis, Frederic already makes it pretty far. He can swim fast, you know where he has to go, so he ends up here in the fallopian tube. Now when he comes closer to the oocyte, another phenomenon comes into play, which is called chemotaxis. During this chemotaxis process, Frederic helps him because she releases a small molecule that Frederic can sense and follow. So this is pretty much like bees or birds follow the scent of flowers and then know where they have to go. So this small molecule is called progesterone. In the next video I will show you what happens when progesterone is released. So this happens here in the middle. Stimulus was released and you see suddenly all the white dots, which are the sperm, accumulate here in the middle where the progesterone was released. We'll do that again. I think it's quite impressive. And all the sperm end up here. So imagine if this would be the oocyte, they would be there, right? So to look into that a little bit further into detail, I will show you this graph. So this pretty much explains how Frederic finds his way. Because what he does is that he simply changes his swimming direction when he feels that the progesterone concentration gets lower. So Frederic starts here, then he swims in this direction, and then here suddenly he realizes, there's not that much progesterone anymore, I should maybe go another way. So he just makes a sharp turn, and swims up here. And then here the same thing would happen. So if he would keep going, like this, in this direction, progesterone would get lower. So he makes another sharp turn, whoop, and then he's already here. So he does that a couple of times, and by doing that, eventually he finds the source of progesterone, which is Susanna. Well, that's pretty smart, right? And I'll show that again because it's so cool. We even made patterns sometimes, but like Mickey Mouse and stuff, but I couldn't get a handle on those videos, unfortunately. So now Frederic is pretty close, and you would think, and he also probably thinks, that he made it. His goal is done, he delivered the DNA to the oocyte. To his big disappointment, the Susanna is not like other cells surrounded by a plasma membrane, so this is a lipid double layer. She's surrounded by an additional layer called zona pellucida. The zona pellucida is pretty much a layer of proteins that are heavily glycosylated. And initially, Frederic is not be able to get through. So here you see an oocyte for real. Here, that black line here is the plasma membrane, the lipid double layer, and then here this hollow ring is the zona pellucida. So here I did fluorescent staining of the zona pellucida and imaged through the oocyte, so you can get an idea of the three-dimensional structure. And that blue point here, that's the DNA of the oocyte. The zona pellucida consists of 3 different proteins, and they are very smartly named as zona pellucida 1, 2, and 3. So zona pellucida 2 and 3 form long filaments, which are then cross-linked by dimers of ZP1, and thereby a net-like, sponge-like structure is formed. So here, in this high-resolution image of an oocyte, you see that it's not a smooth surface, it's rather, it looks a little bit like the moon, actually. There are a lot of hills and cavities in there. There are sperm hanging out on the surface, and it's actually really hard to see them. All those spaghetti-looking structures here, those are all sperm, and here I pointed one out so you can actually see the head here, and then here's the tail, and then there's another one coming. You already know that Frederic is pretty smart, so of course he also finds a solution for that problem, and the solution for that problem is, that's probably only something Germans understand, so Anna, you have to laugh now. here? Yeah, good. So the solution for that problem is an increase in the intracellular calcium concentration in sperm. And this calcium concentration increases when Frederic binds to the zona pellucida. One can follow that increase in calcium by performing so-called calcium fluorimetry. This means that I take a fluorophore, so that's a protein that gives off fluorescence, and that's a special protein that is only fluorescent when it's binding calcium ions. So those fluorophores are then loaded into Frederic. So whenever his intracellular calcium concentration increases, I can detect that as an increase in fluorescence. So here in this video, this is his basal fluorescence. There's a little bit of calcium there. And now soon, zona pellucida is added, and you see that he starts lighting up. So this represents that his intracellular calcium concentration increases. And unfortunately, the head is cut off, so the head is here, the tail is here. So if you look really closely, you can appreciate that the whole increase actually starts here from the back and moves all the way to the front. If you now combine Frederic with a lot of his brothers, this calcium signal looks like this. So here the change in fluorescence again resembles an increase in calcium. So here at this point, the zona pellucida is added. So see that the fluorescence, so the calcium goes up, and then it very quickly goes back down. So this is what we call a transient signal. This short transient signal is enough though to evoke the so-called acrosome reaction. The acrosome is a structure on the sperm head, so that's why Frederic was always wearing a hat, because he has that structure sitting on top of his head. And this acrosome is filled with enzymes, but this time so-called hydrolytic enzymes that digest other proteins. This is pretty much like the enzyme in your stomach that digests the food. So now, when the zona pellucida is added, you can start seeing that this structure dissolves. So there are holes here, then there are more holes, it's pretty much already gone here, and then after this acrosome reaction is complete, the whole structure is gone. So by dissolving this structure, the hydrolytic enzymes that are symbolized here with the scissors are released, and those enzymes then digest the zona pellucida. So pretty much make hole the zona pellucida that Frederic then can go through. So in this image, you see a sperm, here is his head, here is his tail, this is the zona pellucida, that starts penetrating the structure. And then you can imagine that this takes a lot of effort. So one of the ideas is that the sperm that come first to the oocyte actually just are there to make room and space for the sperm that are coming next. And it could actually be that some sperm that was somewhere down the line is just lucky, he gets there, the path is open, and he can get right through. So pretty much they're sacrificing themselves for the other sperm that is coming. So this schematic then shows the whole scenario when sperm and the oocyte finally meet. So here we have the binding of the sperm to the zona pellucida. This is actually really important, so it's not just to make Frederic's life harder. This is actually important because this guarantees that only a sperm from the same species can bind to the oocyte. So that's the reason why no mouse can fertilize a horse or whatever gross things could happen. So this makes sure that only a mouse sperm can fertilize a mouse oocyte. So we have the zona pellucida binding, then the acrosome reaction is evoked, then you see here that the sperm start penetrating, and then finally Frederic reaches his goal and he can fuse with Susanna. And then what actually happens is that the whole machinery, the tail and the plasma membrane, stay outside, and only the DNA goes into the oocyte. So then as soon as one sperm has bound to the plasma membrane of the oocyte and has gotten his DNA in, the oocyte is pretty smart because it starts again releasing enzymes that in this case further digest the zona pellucida. And thereby the whole net-like structure just gets much more tighter, and thereby no other sperm can get in. So this ensures that only one set of female DNA and one set of male DNA ends up inside the oocyte. If there are multiple sets of DNA accidentally getting in, then that causes an error, so to say, and the oocyte dies. So in this video now, this shows how a sperm is doing his job, how it's fertilizing the oocyte. So you have to be really careful because the sperm is really, really tiny compared to the oocyte. So the sperm will come from here. It's wiggling about. There it is. So you see the final step, we're really, really fast. So now for a while nothing happens, only the DNA of the sperm is in there now. And now the DNA gets thicker and thicker, and you can start seeing the male and the female DNA is so-called pronucleus. So this is the male one, this is the female one, and those two fuse. So this means that the DNA of the male and the female fuse together, and then the cell starts dividing. So we had one cell, suddenly we have two, then soon we're gonna get a third one. There we go, and then there will be a fourth one. And this continues many, many times till the finalized embryo is there. So we're going to show this to you again. This is the sperm down here. Here he's going in. This happens really fast, so you have to pay close attention when we'll play it again. And those down here are all the unfortunate sperm that also made it to the oocyte, but are now not getting in anymore because that one lucky sperm, hopefully in our case it's Frederic, made it in. So now we have the DNA fusing again. And then it's dividing the first time. And the fourth time. Should I play it again or are you good? Yeah, there it is again. So the sperm fuses, like boom. So here you can see again what happens following. So we have that one oocyte here, and then it divides into 2 cells, 4 cells, 8 cells. At some point, when there are too many cells that you can't count anymore, we call it morula. And then here in the blastocyst stage, it's already defined which cells become skin, which cells become bone, which cells become brain, so to say. So Frederic made it. That's great. The question you get asked the most when you do science is, when do you get a proper job? And then also, what is this all good for that you're doing? So I thought in the end, after we successfully brought Frederic to the oocyte, I thought I'll give you 2 examples why I'm doing this. The first thing is, of course, you saw that the whole process is highly, highly complex. And it's amazing how little is understood, so it's really important that we dig deeper and can follow the whole process. Then there are a lot of couples out there that have enough sperm, but are still not able to get pregnant. So for those sperm, something is wrong during the capacitation process. So if we understand better what's going on, we can then also individually treat those patients. Then the last reason is contraception. This is a condom that was discovered by the Romans 2,000 years ago. I know it doesn't look like it's working very well, but so you can see that in terms of contraceptive method, nothing has really happened since 2,000 years ago. The only method we have now in modern medicine is vasectomy, so you just cut the vas deferens in the male, but this is of course a terminal process, so this is not an option for everyone. So since SAC is so crucial for this capacitation process, we thought that we might use the enzyme and develop some inhibitors that we could then use as contraceptives. We have those inhibitors laying around in the lab for a while already, we just decided to make them more potent. So the idea is that this inhibitor then blocks SAC, and then no CAMP is produced, and then this whole capacitation process is not initiated anymore. And we were surprised ourselves, but it actually already works quite well. So here you see videos of control sperm. They're just swimming about nicely. And those sperm here were treated with inhibitor. You see that only few of them are still swimming, and then most of them actually have stopped. And the reason for that is that they ran out of energy at some point. So you can imagine that it's not very likely that those sperm make it to the oocyte at the end of the day. The ultimate goal, of course, is to test whether male and female mice become or female gets pregnant and they get offspring. So the experimental setup for this is really easy. I inject the inhibitor into the male, and then I mate it with the female overnight. Then I take the male back out so that I have a defined time point. And then 21 days later, I check whether they got babies or not. So this is the first result as we got. So you see in the control, I got 60% pregnancies. I made it through the whole presentation without bar graphs, so that's the only one you have to see. So this is the control, we get 60% of pregnancies, and we add the inhibitor, we get it down to, I think it was like 15 or something like that. It's not perfect yet, I know, but this is how it goes with science. You need a long breath and it doesn't work perfectly the first time you do it. But you see that we were significantly able to decrease the pregnancy rate. So I think we are on a good path. We'll just have to optimize the protocol and get more potent inhibitors, and then we hopefully bring this down to 0. So with that, we'll come back to Frederic and Susanna. So happy ever after, hopefully. I thank you all for your attention. Thanks for coming out. And if you wanted to know something about sperm, just fire away.
Awesome talk.